Okay, so we have been looking at the Lebesgue integral of non-negative simple functions, from which we also went ahead to define the Lebesgue integral of a non-negative measurable function. So now we will move on and deal with arbitrary measurable functions, and therefore we can't do it for all functions, of course. So we want to now look at integrable functions. So these are functions for which an integral can be defined. So XS mu measure space, and you consider f a measurable function on x. Okay, so now we can of course write f as f plus minus f minus, the positive and negative parts, and since each of these is non-negative and you expect the integral to be linear, therefore the only possible definition you can give of integral f d mu over x equals integral f plus d mu over x minus integral f minus d mu over x. But there is a catch. If both these happen to be infinite, then the integral of f plus and integral of f minus, if they are both infinite, then we will not be able to define this difference in a meaningful way, and therefore at least one of them has to be finite. In this, so we make the following definition: XS mu measure space and f a measurable function. The function is said to be Lebesgue integrable. We will just say integrable in future. We want if integral over x mod f d mu is less than plus infinity. So such a function is said to be integrable function. Now mod f, if you remember, is f plus f minus. So if the integral of mod f is finite, so f integrable implies integral f plus d mu over x and integral f minus d mu over x are both finite, and therefore there is no difficulty in defining the difference which we have. So if f is integrable, we define integral of f d mu over x as integral f plus d mu over x minus integral f minus d mu over x. So of course, as I told, if it's enough if one of them is always finite, but then it's a very we can't go on make a definition because sometimes this may be finite, the other times f minus may have finite integral and so on. Therefore we look at integrable functions, namely functions for which you can definitely define the integral, and that is those for which both are finite, and therefore that is integral of mod f is finite. So at this point we can consider all complex valued functions also. So f from x to c is a complex valued function. Let us write it as in terms of the real and imaginary part. So u equals the real part of f and v equals the imaginary part of f. Therefore both u and v are real valued functions. So we say that f is measurable if u and v are measurable. F is integrable if mod f is integrable. Same definition. So if f is integrable, then mod u is obviously less than or equal to mod f, and mod v is less than or equal to mod f, and therefore this implies that f integrable, then u and v are also integrable. And now we can define integral f d mu over x as in by the linearity question again. So u d mu over x plus I times integral over x v d mu. So generally we've been in notation. So as long as there's no confusion, namely there's only one space and so on, and we will always write integral over x f d mu. But in case you have, say, two variables r or c, etc., and you have a function of two variables, and we want to define an integration of this with respect to one of the variables. So the measure, the space would be xs mu. In that case, we write integral f of x d mu x. Okay, and this will say the variable with respect to which we are integrating. Okay, that's just a question of notation. So now we can prove in full generality the linearity of the Lebesgue integral, which is the most important property. So theorem: xs mu measure space, f and g integrable complex valued functions, alpha beta in C, then alpha f plus beta g is integrable, and integral of alpha f plus beta g d mu over x is alpha integral f d mu over x plus beta integral g d mu over x. Okay, so this is the full linearity of the Lebesgue integral. So proof. So clearly alpha f plus beta g is measurable. And mod of alpha f plus beta g is less than or equal to mod alpha times mod f plus mod beta times mod g, implies alpha f plus beta g integrable. So step 1, integral over x f plus g d mu equals integral over x f d mu plus integral over x g d mu. So without loss of generality, we can assume fg real value, because anyway the complex, you just have to break it up into real and imaginary parts and define the integral, and therefore it's enough to prove for the real case. So let us say h equals f plus g, and then we write h equals h plus minus h minus, f equals f plus minus f minus, and g equals g plus minus g minus. So h plus minus h minus equals f plus minus f minus plus g plus minus g minus, and therefore you get h plus plus f minus plus g minus equals f plus f plus plus g plus h minus. So for non-negative functions, we know that you can, if the sum of the integral is equal to the integral of the sum, so you get that integral over x h plus d mu plus integral f minus d mu plus integral g minus d mu is same as integral f plus d mu plus integral g plus d mu plus integral h plus d mu h minus. Because all these functions are non-negative, and then for non-negative functions we have already proved that if you have a sum of non-negative functions, then the integral of the sum is sum of the integrals. Okay, so we have this. Now everything is finite. So we can rearrange. Therefore, integral over x h plus d mu minus integral h minus d mu equals integral f plus d mu minus integral f minus d mu plus integral g plus d mu minus integral g minus d mu. That is integral of f plus g d mu, this is h, remember, equals integral f d mu plus integral g d mu. So step 2, we have to show that integral alpha f d mu over x equals alpha times integral f d mu. If you do this, then step 1 and 2 together will complete the proof. Okay. Let me put c here, where c is a constant belonging to c. So if c is non-negative, that means a real number which is non-negative, then clearly star is true by definition, because you know for non-negative functions you have, and then the integral is defined using the real and imaginary parts, and also for each using the positive and negative parts. So for instance, if f is real, then you have integral f d mu cf equals integral c f plus d mu minus integral cf minus d mu, because cf equals cf plus minus cf minus, and these are the positive and negative parts of this function cf. And therefore this is for positive functions, we know that this is true, d mu minus c times integral f minus d mu, and therefore this is true. Therefore star is true for non-negative things. Now let us take c equals minus 1. Then what is minus f plus? This is nothing but f minus, and minus f minus equals f plus, because minus f equals f minus minus f plus. Okay, so this is how these are the positive and negative parts, and therefore you have this. So obviously integral minus f d mu over x is equal to integral f minus d mu over x minus integral f plus d mu over x, which is equal to minus integral f d mu over x. So it's true also for this. So this is true. Therefore star true for all c real, enough to show star true if c equals I, because then it's true for all complex numbers also. So okay, you have f equals u plus iv, and therefore if is nothing but minus v plus iu. Okay, so integral over x if d mu is equal to integral minus v d mu over x plus I times integral u d mu over x. And if I pull out the I, so this can be written as minus integral over x v d mu plus I times integral over x u d mu. And if I pull out the I, this becomes I square is minus 1, so this becomes integral u d mu plus I times integral v d mu is equals I times integral f d. And therefore this proves for all constants, and therefore the linearity is completely proved. The next theorem which we are going to show is again very important, because every time we want to estimate an integral, this is the first step which we will use. So xs mu be a measure space and f a complex valued integrable function. Then modulus of integral over x f d mu is less than or equal to integral over x of mod f d mu. This is a very, very fundamental inequality which always will come in every time you want to estimate an integral. So proof. So if you have z in C, then you can write z equals mod z times e power I theta, the polar decomposition, and therefore you have mod z equals e power minus I theta times z, and mod of e power minus I theta, remember, is always equal to 1. So let mod alpha equal to 1, alpha in C, such that mod of integral over x f d mu is alpha times integral f d mu, and let u equal to the real part of alpha f. Then u is of course less than equal to mod u, which is less than equal to mod of alpha f, and that's less than equal to mod f. So implies u is integrable. So modulus of integral over x f d mu is nothing but alpha times integral f d mu. But then we know by the linearity this is nothing but integral of alpha f d mu over x. Now this should be written, how is this written? This will be integral u d mu plus I times v d mu, where v is the imaginary part. But then that is equal to 0, because you know already that this is real, and therefore there can be no imaginary part for this integral. So this is equal to integral over x u d mu, but u is less than equal to mod f, so that's less than equal to integral over x mod f d mu. And so this completes this proof. And so next time you are going to look at another limit theorem, like the monotone convergence theorem. The next theorem which we are going to prove will be an all important limit theorem in Lebesgue integration. It's one of the high points of the theory which we will see next time.